All right, so in section 4.2, we talked about exponential functions. Today we're going to talk about their counterpoint, and that is logarithmic functions. This word right here is logarithmic. It has the word logarithm in it. A logarithm is the inverse of an exponent. So a logarithm will undo an exponent will undo a logarithm, and what we're going to see today is sort of that. Really, a logarithm is just another way to write an exponent. It's sort of writing it in its inverse form, okay? Here is the definition of a logarithm. If you were to write something down in your notes, you're going to see this a lot today, okay? So y equals log bx. The b is the base. Y equals log base b of x, that's how that's read, is the same thing as b to the y equals x. Just look at where those pieces are in relation to each other. B is the base of the log, b is the base of the exponent. Y is on this side of the equal sign, and it becomes the exponent. X is with the logarithm, and it goes to the opposite side of the equal sign. We're just looking at a trend here, right? We're just looking at a form. We're going to try and write things from logarithmic form into exponential form, and vice versa, from exponential form into logarithmic form. I have all of those definitions are down here, right? So b is the base of the logarithm. X is called the argument of the logarithm. We don't use that vocabulary very often, but x is the argument. You'll hear me talk a lot about the base and not so much about the argument. Here's that form again. So in these problems, what we're trying to do is, you know whether your equation is in logarithmic or exponential form because it's either going to have a logarithm, right? Log is how we write a logarithm, or it's going to have an exponent. So this has an exponent. That's in exponential form. In these problems up here, we're trying to write them from logarithmic form. We're trying to write them in exponential form. So we're trying to go from this form into that form. You can go back and forth. Notice these arrows go both ways. You can write it back and forth either way. If I was trying to do this equation, what I'm looking at is my base of my log becomes the base of my exponent. So my 2 is going to become the base of my exponent. Like I was saying on that other slide, the thing on the opposite side becomes the new exponent. The thing on the opposite side is going to become my new exponent. And the item that was with the logarithm goes to the opposite side of the equal sign. So the item that was with the logarithm, the 16, is going to go to the opposite side of the equal sign. Notice that I ended up with an equation that is true. 2 to the 4th is 16. I could check that in the calculator. I just wrote this in exponential form. It's the same exact equation, just written in a different form. All right, how about this one? Log base 10, 1 over 100 equals -2. I would pause and see if you could do it. Writing this in exponential form, my base is 10, my exponent is -2. The number on the other side is 1 over 100. This is the same equation, just written in a different form. Again, take a second, see if you can do this one. The base is 7, the exponent is 0, the other side is going to be 1. I can reverse this process, right? So here I could take it from exponential form and write it backwards into logarithmic form. Just again, using this exact equation here, this relationship between logarithms and exponents. It's exactly what we're trying to do here. So we're trying to go from exponential, and now we're trying to go back to logarithmic form. Let's see how we can do that. So the base of my exponent becomes the base of the logarithm. So I can write log base 3. The number that was on the opposite side of the exponent is going to go with the logarithm. So here the number on the opposite side, the 81, is going to go with the exponent. And the number on the closest side of the exponent goes to the other side. And that is my logarithmic form. It gave me the problem in exponential form. I wrote it in logarithmic form. Take a second, pause, and see if you can do these other two. This one would be log base 10 because the base is 10. 1 million. Make sure I have enough zeros there. Equals 6. Notice in logarithmic form, here's one thing that you do need to notice. Everything's on the same plane. Everything is flat. The only thing different is the 3 is a subscript, okay? Everything else is flat. The same thing with an exponent. Everything is flat. It's on the same line. The only difference is that y is a superscript. Here, everything is on the same line except for the 3. Let's try this last one. I could write log base 1/5 of 5 equals -1. All I'm doing for all of these is going back to this original formula up here, this relationship between logarithms and exponents. If we want to evaluate an expression, what we're going to do is we're going to type it in the calculator, right? Or hopefully type it in the calculator. We'll have a way in just a little bit where we can use the calculator a little more. For now, I think just writing these in exponential form is going to help you see what the answer is going to be without having to use the calculator. So for this one, in example A, log base 4 of 16, if we were to rewrite that in exponential form, right, using the same relationship we have been, what I could say is, if I said this is equal to x, I want to know what x is. I could rewrite that as 4 to the x equals 16. And then I could just guess around in my calculator. Like I said, in a little bit, I'm going to give you a little bit of a better way to do this, right? But for now, I could guess 4 to the 1, is that 16? Nope. 4 to the 2, is that 16? Yes, it is. So then I know that x has to equal 2, because 4 to the 2 equals 16. I'm using my calculator to figure that out. On part B, I can do the same little trick here. If I set that equal to x and I want to know what x is, here, let's use a different variable. Let's say I wanted to use m, just so I'm not using x's everywhere. I could say, if I wrote that in exponential form, 2 to the m equals 8, and I would just check in my calculator, 2 to the 1, nope, that's 2. 2 to the 2, that's 4. 2 to the 3 is 8. That means m must equal 3. Try that last one down there. And I'm going to use variable z. I would write 1/2 to the z equals 8. And I would try numbers until I got it, right? This one's a little bit trickier, but you're going to have to go into the negative numbers. Try some negative numbers. I'm finding with my calculator that 1/2 to the -3 equals 8. So then z must equal -3. Here's an opportunity for you to try some of these. I would pause. I'm going to count to 5 before I unfreeze. On this first one, if I set it equal to x, 5 to the x is 125, x is 3. In the second one, set it equal to x, 3 to the x is 81, then x must equal 4. That's again just guessing and checking in the calculator. The third one, the same way. We know we're going to get a negative number because we ended up with a fraction, but 4 to the -3 is 1 over 64, so x must be -3. We do have two special logarithms. They're called the common log and the natural log. The common log has a base of 10, and we just write it as log x. Anytime you just see log x or log 10, log whatever, right? If I just saw in my problem log 5, it's an understood base 10, just like saying x is the same thing as 1x, right? If I don't have anything written there, that's an understood base 10. That's a common log. A natural log looks like this. It would say ln of 5. Now the 5 can be any number. It doesn't have to be a 5. This has an understood base of e, where e is that number in the calculator, the same exact number that we used last time. It's e. It's on the left-hand column there. It's just below the log button, in fact. So if you look on your calculator in the left-hand column, you actually do have a log button and an ln button that you can use, right? So if you just had, for example, evaluate log of 10,000, notice in your calculator you do have just a log button. That was not the same back here where we don't have a log base 3 button. We can't just type log base 3, log base 4. We can't type those in the calculator. But we do have special buttons on the calculator that let us calculate common logs and natural logs. So you'll see on the left-hand column, the top two buttons basically are log and ln. If you type in your calculator log 10,000, you should get 5. That's literally just typing in the calculator. If you type log 0.001, that's the same thing as negative 3. ln e to the 4 in your calculator will give you just a 4. ln 1 over e in your calculator will give you a negative 1. These are just calculator problems here. Any problem that just has a regular log or a ln, a common log or a natural log, you can really use your calculator a lot, pretty heavily on those. These say approximate. They're just wanting a decimal, and we'll just take each decimal to 2 decimal places. So if I did log 5809 in the calculator, it gives me 3.76. Log 4.6, log 4.6 times 10 to the 7 is going to give me 7.66. Log of 0.003. 0.003 is negative 2.52. ln 472, that's the other button on the calculator, the ln button, natural log button, is 6.16 if I round it. ln 0.05, 0.05 is negative 3, almost on the dot. If I round it to 2 decimal places, ln of square root 87 is 2.23. Again, these, when we're trying to approximate common logs, natural logs, those are in our calculator. Here are some basic properties of logarithms that we can use to solve problems. Notice that it does have an example of each on the right-hand side. Anytime you have log base any base of 1, log with any base of 1, it's always going to equal 0 because anything to the 0 equals 1, right? So for example, log base 5 of 1 equals 0. Log base 10 of 1 equals 0. Log base e of 1 equals 0. Log base pi of 1 equals 0. Log base anything of 1 equals 0. Log with the same base and argument, so log base 10 of 10 is always going to equal 1. Log base 5 of 5 equals 1. Log base pi of pi equals 1. Anytime you have the same base and argument, it's going to equal 1 because anything to the 1 power equals itself. If you had log base b of an argument to a power, as long as the base and the argument match, the power is going to be your solution here, right? Because b to the x equals b to the x. And it reverse that. If I have an exponent with a base to a logarithm with the same base, the argument of that logarithm is going to be your answer. Let's look at some examples down here. I think this is going to help. So I'm basically going to look at my examples and try and match them up to one of the properties. So A looks like it matches with property 3, right? Log base 3, 3, 10, B and B match, then 10 must be our answer. B, that also matches, even though it doesn't look exactly like it, with property 3, because that's the same thing as log base E of e to the 2, right? ln is the same thing as log base e. It's an understood base e. That means our answer must be 2. Log base 11 of 11, that looks like property 2. That's got to equal 1. See if you can get the rest of these. D looks like another property 2. That's the same thing as log base 10 of 10. It gives us 1. E looks like property 2. No, it looks like log base square root 7 of 1. It looks like property 1. So it must be 0. ln 1, that looks like property 1. That's the same thing as log base e of 1, right? All right. G looks like property 4, and so our answer is going to be c squared plus 4. H also looks like property 4 because just a regular log with no base, remember it has an understood base of 10. So that's 10 to the log base 10 of a squared plus b squared. Property 4 is going to give us a squared plus b squared. If we want to graph logarithmic functions, we can follow the same setup that we were doing in the last section where we were trying to graph exponential functions. We can just start putting in some numbers and see what happens. I think this is going to give us a good idea of what our function looks like. First, if we put in any negative number, right? So we haven't tried this yet, but log base 2, let's find some numbers that work well, right? So we need powers of 2. Log base 2 of, if I try 0, if I try 1, 2, 4, 8. We can go back and think about the same way that we were doing. If I said log base 2, let's say x is 4 first. Log base 2 of 4. Then 2 to the y equals 4. Then y must equal 2, right? If I said the same thing, log base 2 of 8 equals y, trying to find what matches with 8. 2 to the y equals 8. Well, 2 to the 3 equals 8. So then y must be 3. 2 to the 1 is 2. 2 to the 0 is 1. Can you find a number where 2 to that is equal to 0? In fact, you cannot. You can never do 2 to a power and get 0. If I try and graph these, this is going to make an interesting shape. I have the point 1, 0. I have the point 2, 1, 4, 2, 8, 3, and I never can make it to 0. And so this one, instead of having a horizontal asymptote at y equals 0, this one actually has a vertical asymptote at x equals 0. The function's never going to touch that. In the same way with exponentials, this one is going to depend on shift, right? It's going to depend on a shift, but it's going to depend on a horizontal shift. So if your graph has a horizontal shift, it's going to shift that asymptote. You could try the same thing with b, right? If we put in 0, it's undefined. 1/4 to the 0 is 1. 1/4 to the negative half is 2. 1/4 to the negative 0.79 is 3. And so just like with exponential growth and exponential decay, we sort of have, if we're putting in a fractional number here, we sort of have a decay model here instead of a growth model. We still can never get to 0. There's no way to ever get to 0. That's an undefined value there. There's no way to put in a number as a power and get 0 as an answer. Notice this one does still have a vertical asymptote at x equals 0 because there was no left to right shift. You know there's a left to right shift if there's something added in the parentheses. So if I had x plus 5, for example, that would shift it left 5. In our case, we don't have anything added or subtracted inside of the main portion of that logarithm, and so there's no horizontal shift, right? That's the only thing that's going to shift that asymptote. This one, all right, here's a good example. The plus 3 is going to shift this one left 3. The minus 2 is going to shift it down 2. We don't have to be super precise on this. But if it shifts it left 3, we know that our vertical asymptote is going to be shifted left 3. So it's going to be here. And we just graphed the function log base 2 of x, right? So if we look back up here at log base 2 of x, this is what it looked like right here. And if we want to take all of these points essentially, and shift them down 2, I'm not going to be precise here. I'm just going to say that it's going to look something like this, right? It's going to be the whole graph shifted downwards. This whole graph right here shifted downwards. It does not stop going upwards. It does keep going upwards, right? It's sort of, the way that I drew it makes it look like it has a horizontal asymptote there as well. It doesn't. It keeps going upwards just very slowly. All right, when we're talking about the domain of logarithms, you can't, if you notice here, there's nothing to the left of that asymptote, right? There's nothing out here. There's nothing out in this region. The entire function is in this region over here. And so if we're talking about the domain is just from negative infinity. No, I'm sorry. The domain is from 0 to infinity. Not including the 0 because it never makes it there. The same thing with the domain for this next one, right? The domain's just from 0 to infinity. There's nothing to the left of that vertical asymptote. On this one, there's nothing to the left of this vertical asymptote still. The whole function is to this right side. And so if I wanted to write the domain, I would write that the domain is from negative 3 to infinity. From the horizontal shift, essentially, which is where the vertical asymptote is, at x equals negative 3 to infinity. All right, if I wanted to write the domain of this one, we need to know where it shifts. And so on this one, since we have 2x plus 4, a negative 2 would make that 0, and so this actually shifts to the left 2. And so just a general idea of the graph, right? We don't need anything super particular, but we have a vertical asymptote at x equals negative 2. This graph is going to be, there's going to be no graph over here, right? And our graph is going to be in this area. I don't know what it looks like, but something like that. And so our domain is going to be everything from there over. So the domain is going to be from negative 2 to infinity. All right, G is a little bit weird, right? 5 would make it 0. Positive 5 would make it 0. So we're thinking positive 5, 1, 2, 3, 4, 5 is our vertical asymptote. And if the trend stands, then we would have everything out here. But in this case, since we have a negative x inside, it actually reflects it over the y-axis. And so we're going to have graph only here, right? Our graph is going to look more like that. This negative sign right there reflects it horizontally. And so in this case, we actually don't have graph to the right. We have no graph to the right. We have graph only to the left. And so our domain is from negative infinity up to 5. And it stops at 5, right? The graph stops at 5. That's it. That's the end of logarithmic functions. In the next section, this is absolutely not it for logarithmic functions, right? I said that's it, but really there's a lot more properties that we can use with logarithmic functions. There's a lot of properties that make simplifying these logarithmic functions easier, and we're going to learn those in the next lesson.